quiz. So we'll move on now to the lecture. I think we finished with this first part. We showed you how to describe, some components used in sequential circuits using VHDL. And again, we will do more. So, for example, for the JK, we will do it in the tutorial. And then we will have more examples as well, or more exercises. Now I'm going to move to the test bench. So as I said in the beginning of this lecture, in the last session, you are familiar with, in the lab, you use the waveforms, which is one way to do to raise the test bench. I don't know why this one doesn't. Yeah. So one way to simulate your circuit is to just use the, you draw the waveforms on using the software. This is A, and then you do B, and then you run the simulation. So run simulation, and then you will get the output. I don't know, whatever the output, C. So the simulator will use your VHDL code, and then it will apply those test cases, we call them test cases, into your VHDL code. So in your VHDL code, you must have A and B as input. And then you must have C as an output, which will give you the result. So this, as I said in the last session, this can be written in a code as well. Another VHDL code, which we call Vhdl Testbench. To do this, we need to use some statements, and those statements are the wait and the assertion statement to generate your test cases. To say, okay, I want A to be 0, and then I want B to be 0, and then I want to keep them like that for 5 nanoseconds, for example. So you will get the waveform that you will get A0. This is A, this is B, and both of them will be 0 for 5 nanoseconds. And then next you say, I want A to be 1 and B to be 0, another 5 nanoseconds. So you will get A1, and then you will get B stays as this, and this is 5 nanoseconds. And here we have another 10 nanoseconds, so another 5, and so on. So this is how you can do it, of course, using those statements. And then I will show you how to put it in a full, test bench. So we have to follow a template, specific template that allows us to do simulation. Right. We start with the wait statement. So the wait statement explicitly specifies the condition under which a process may resume execution after being suspended. So as you can see here, we have the word process. So this means the wait statement is used inside the process. So we have process. And then, do you remember when we talked about the process, the first time I said we have sensitivity list, and this is optional. When we write a VHDL code, we always use the sensitivity list. We always have signals to be there that will trigger the process. When we write a test bench, usually we don't put anything in the sensitivity list, which means the process, if I do this, a process like this, process, and then I will do x is equal 1, y is equal 0. If I do this, and then what will happen here? This means that those will be executed continuously. So I'll just try to explain a process without sensitivity list. So this means the process is always triggered and it will continuously be running. If we have a sensitivity list, this will control our process when it will run and then when it will stop. So if there is no event on the signals, it will stop. It will be triggered whenever there is an event on one of the signals, and then those will be executed and then back, and then wait for the next event, and so on. But if we don't have anything in the sensitivity list, this means that whatever inside the process will be continuously executed. And then, of course, we can use the wait inside this process to suspend it for a specific time. So here we can specify a time, or we can specify, so we have different forms. So we can specify a time. We can put a signal, wait on clock, for example. So this will wait until there is an event on clock. So this is similar to having the clock in the sensitivity list. Or it could be wait until a condition is true. So it will go inside and then it waits until a condition is true. And how does the condition become true? Of course, if we have another process or another statement outside the process that will change the values of whatever we want to check. So the values will be changing outside this process, but the condition will be checked inside the process and be waiting until the condition is true. So these are some examples here for each one. For example, for the first one, so I can say wait for 10 and then specify 10 nanoseconds, and this is valid in Vhdl. So you can put microsecond, you can put nanosecond, second, and so on. So wait for 10 nanoseconds. The other case, wait on clock and reset, for example. So you can put the ports like that. The third example, wait until A is more than B. So those are the three options for you to use if you want to use a wait inside the process. Right, now how do we use this wait if I want to generate cases, if I want to do simulation? And this is a very good example here about a clock. Let's say that I designed a flip-flop. I have clock, we have Q, and we have Q bar. And remember, and this is very important, when we do simulation, in the test bench, we care about inputs. I don't care about outputs. I care about the inputs. So I need to give values for the inputs and clock. And then I will run the simulation. Once I give values for the and clock, do you remember? So in the previous lecture or in the previous tutorial, we gave you this and we say, okay, what's if D is like this? And then we have clock, what will be Q? So this is the question. As a human, and you know how does a flip-flop work, you need to give the correct Q here. Now, this Q, when we do simulation, you already write the code for a flip-flop. So we ask you first to write the code for a flip-flop. But you will provide the code. How do we know that this is correct? This is a really flip-flop and it will work as a flip-flop and not as something else. So we need to test it. How do we test it? We need to write a test bench, or you can use as you did in the lab with the waveforms. So now we are talking about how to write a test bench. So to write the test bench, I need to provide inputs. The simulator will take this test bench, the inputs defined in my test bench, and it will apply them to the Vhdl code that you wrote. And then it will provide the outputs based on what you wrote. As a user or as a designer, you will observe the output. You will check the output Q. Is it correct for the scenario that you gave or for the test cases that you gave? Is it correct? Is it the Q what you expect from a flip-flop? If it is not correct, this means your Vhdl code is wrong. So you need to go back to your Vhdl code and see what's wrong. And then you need to repeat the process and you simulate again. Right. Now, if as I said, if I want to simulate a flip-flop, JK or D flip-flop, one of the inputs is a clock. So I need to generate a clock. In my test bench, I have to make sure that I have a clock. When I run the simulation, I have a clock. And the clock, as you know, is a continuous signal. And this is how I can generate it. So I can write a process inside my test bench. I can write a process like that, and then do begin, and then clock is equal 0. Wait for 5 nanoseconds. What does it give me this first? So the process will be in execution, always in execution. Sorry, just wanted to use a different color. The process is always in execution. So it will start from here. Clock is 0, so we will have clock 0. And then it says, wait for 5 nanoseconds. So clock is 0, and it stays 0 for 5 nanoseconds. At this time, so we start 0 nanosecond, 5 nanosecond. And then after 5 nanoseconds, we go to the next statement. It says clock is equal 1. So clock goes to 1. And then it says next, it says wait for 5 nanoseconds. So we will have another 5 nanoseconds, which means this is 10. And then after finishing this, so it will go back to beginning and then execute this again. It's a loop. And it's controlled by this wait. So this wait will give us the time for clock to be 0 and the time for clock to be 1. And this will give us the frequency, right, of my clock, or the period of my clock. So I will get 0 and then 1 and then 0 and then 1, and it's continuous signal. And then if you do the simulation, you can see a normal clock with a period of, what is the period here, is 10 nanoseconds. So if I want a period of 20 nanoseconds, I can just replace this 5 with 10. If I want a period of 5 nanoseconds, I will just replace this 5 with 2.5, and so on. Is this clear? So I can do the same if I want a D. Let's say I want D to have this form. For clock, for example, this example that I gave you here. Is this clear?
Yes, Doctor.
Okay, good. Now let's say that I want, so if I want to do a D flip-flops, and then I have D and I have clock. Those are the two that I need to consider in my test bench. And then let's say I want to do this. I want D to be like that. And this will be my test. So I want to generate this clock, and we already showed you how to generate this clock. And then next, I want to generate this D as well to simulate the same component. So I want to simulate this D flip-flop. So within the same code, within the same test bench, Vhdl Testbench, I need to add, this is one solution. I need to add another process. So I can have, for example, another process here. So I will have two processes. So this process is for clock, and then I will have a second process for D. And those two processes will be running in parallel. So each one will generate a waveform for me. So this first process will generate this waveform for me, and then the next one will generate this one. If I have another input, I can add another process, and the third process will generate the other input for me. So now I want this process. So how can I? And then I will do begin, and then do you see we start here? D is 0, so I can just write D is equal 0, and then we wait for 10 nanoseconds. This is 10 nanoseconds, right? So wait for 10 nanoseconds. So this will give time. So we start from here, and then D is 0. It stays 0 for 10 nanoseconds. And then next, D goes to 1. And then another wait. So I can write it here. Wait for another 10 nanoseconds here, right? Because this will be 20, right? Wait for 10 nanoseconds. Is this clear? And then next, D goes to 0. And as you can see here, if I want to leave it 0 forever, I can just do wait. Yeah, this is not periodic signal. This is not like the clock. So for the clock, we did this, and this will be repeating. Now, for this D, if I want to finish with 0 and leave it 0, I will just do wait without time. So and this will wait forever. So which means this process will stop here, and that's it. And of course, it will give me what I want. It will give me this waveform. And by the way, when you run the simulation, you can specify for the time for which you want to see the waveforms. So you can say, okay, I want to see the waveforms for 100 milliseconds. So you can get 100 milliseconds of your simulation. You can get 50 milliseconds. You can specify this when you use the simulator. Is this clear?
Yes, Professor, I have a question.
Yes, go ahead.
Isn't the time period 15 nanoseconds for the D? I mean,
Which
the first part for the D isn't 15, not 10.
Oh yeah, it's 15. Yeah, okay. I think you got my point anyway. Yeah. So
Yeah,
yes,
yeah.
it's 15. Yes, you are right. And again here it's 30. So it's yes, correct. Yeah, well spotted. Yeah, and this is 30. And then the last one I can if I don't want to specify time, I don't specify it. If I specify it, what will happen if I put here wait for another? Sorry, 15 again, not 15, 15, 15. If I do 15 again here, so what will happen here? In the last one,
it will be the last one will be 0 for 30 nanoseconds.
15. It will be 0 for 15, and then what will happen?
And it will run again for 15 seconds. It will the code will run again. It will be periodic.
So this will be repeated. So what we have here, it will be repeated again, and it will be repeated again and again and again. Yes, this is what will happen. Good. Do you get the point? So this wait will help us to generate our cases, test cases, for the time that you want. Any time you want, any shape you want. Is this clear? So so another example, if let's say if I want to do, I'm spending time here because this is important, and it's good for you to understand it. Now if I have an AND gate, let's say I write the code for an AND gate. I have A and B and C, and then you have the Vhdl code and you know how to write it, and then I need to go and write Vhdl Testbench. So I have two codes. I have the main code for the AND gate, and then I will have the Vhdl Testbench. In the Vhdl Testbench, let's say that I want to have those cases. So basically for an AND gate, I can have those 4 cases, right? 0, 1, 0, 1, and then I can have 0, 0, 1, 1. A and B. I can do this with two processes, one process for A and one process for B. Or I can do it with one process only. I will show you both solutions. So if I do two processes, I think now you understand for the, I will use the first one, process, begin, and then I will do A is equal, we start 0. Let's say this, I want this 5 nanoseconds here. 0, and then you do wait for 5 nanoseconds, right? And then we do A is equal 1, and then wait for 5 nanoseconds, the same. And then we do A is equal 0, wait for, and I can do again A is equal 1, wait for, or just wait at the end, because I just need it 1 and then that's it. I covered all my cases. This is for A, and then I can repeat the same for B. For B, I have just two cases, so I can just do it. So another process for B, process A, begin, A, oh sorry, B is 0. Now I will wait for 10 nanoseconds for B. And then I will do B is equal 1. And then I can just do wait for the last one. And that's it. The two processes, both of them, or each one will give me, the first one will give me A and second one will give me B. And then I run the simulation and I can just observe for the first 20 nanoseconds are enough. Right? 20 nanoseconds are enough for me to see my result, right? I have the 4 cases, so this is enough. So I did it with 2 processes. You can do it with 1 process only if you want. Where in this process you put both. So, and this is what I'm going to do now. So process, 1 process, begin. So we can do A is equal 0, comma, B is equal 0, wait for 5 nanoseconds. Right? So I do this first, A and B, and then I will do A is equal 1, B is equal 0. Again, wait for 5 nanoseconds. And then I did this, and then I will do A is equal 0, B is equal 1. Again, wait for 5 nanoseconds. And then I will do the last one. A is equal 1, B is equal 1. I can just put wait here. Even if you put wait for 5 nanoseconds, it will work. So this will repeat again, and that's it. This is one process. So you can do it with one process or both in one process, or you can have separate processes, and both solutions are good and are correct. Right. I hope this is clear. Another good thing with the Vhdl Testbench is this assertion statement. So this will allow you to check the output. I mean, as a user, you know what is the expected output. So for example, if I do like this, again, I'm giving the example of AND gate, yeah? So AND gate. So I do A is 0, oh sorry, A is 1, B is 0, and then I will do wait for 5 nanoseconds. So now, at this time, what should be C? You know it's an AND gate. You know we are trying to simulate an AND gate. You are the designer, so you know what should be C, right? What should be C for this case?
0.
C should be 0, good. And as I told you, the simulator will give us the waveform for C. We don't care about it. But in a test bench, as designer, you know what is the expected output. You say, with this assertion statement, is like you are telling the simulator, if you don't get C equals 0, then show me an error. And then the simulator will do the simulation, will use your code, your Vhdl code, with your test bench. And then if it gives an answer is 1 instead of 0, then it will show you an error on the the software tool, the message box, that you down, that you see, where you see the warnings, the errors when you do the compilation, when you compile and you see errors, so you can see is there. And as you can specify the message that you want to display. So you can say, oh, there is an error in the first test case, and this message will be displayed for you. How do we do this? We do it with this assertion statement. So you put a condition, assert, and the condition is this one. So you put C equals 0. So it's like you are asking the question, is C equals 0? Now, if the condition is false, if it is true, then there should be no error, right? If C is 0. If C is 0, then it's good. This is what we are expecting, and this is what the simulator got as well from my code. Now, if the simulator gets 1 instead of 0, this means there is an error. In this case, it will display what we put here. We put a string here, report, and then you write whatever you want here. Any message that you want is for you. You are the one that doing the simulation. It's a message for you. So for example, if this is the first test case, you can say there is an error in the first test case. And then you specify the severity. Severity here, I talk about errors, and this is usually where this assertion statement is used. It could be used even for warnings. So you can write just a warning. You can have it as a note for you. For example, to say, okay, test case 1 has passed successfully, test case 2 has passed successfully, and so on. So you can put it as a note. So severity, you specify here, whatever you can specify it as a note, as a warning. What most of the cases is used for errors. And the good thing with this is when it gets an error, it will stop the simulation. It will not go for the next cases. So you don't have to waste your time waiting for the simulation of the whole design, especially if you have a big design. You don't need to wait until you test all cases. So you can just, whenever there is an error, it will stop the simulation. I hope this is clear. This is an example here. And remember, so again, I did the case for C is equal 0. Assert C is equal 0 as the example that I gave you before. What does this mean? This means that I will guess this error. Case 1 returns an error. This is a message that I wrote. So case 1 returns an error. When does it return the error? If C is not equal 0. So it's not when the condition is true. And this is very important, right? When the condition is true, this means the simulation is fine. So this is what we are expecting. So it's good. But it will display the error if this is not 0, if C is 1. And then we specify the severity here, error. So this is a simple example how to include assert in your test bench. I mean, if you want to add it, it's fine. If you don't want, then you just run the simulation and then you will observe the output at the end. So you need to check the output, the waveform of C. So you go and check C and you observe, is it correct or not? So assertion is another option or an additional thing that you can add in your test bench. And again, it's very important when you use it, and you need to be careful. So you should know exactly what you are expecting, because if you put something wrong here, so let's say that the expected output is 1, and by mistake you put 0, and you run the simulation, so you will think that there is an error here, while the error is you who made it when you were at the test bench. Is not, so the error is in the test bench, not in the code. I hope you get my point. And I will show you this later on with a simple example. Again, this is an option that you can add to your test bench, but the most important one is this one. What we covered here is how to generate your cases. Right, now I will just move to where do we put this process? How do we put it? The processes that we talk about here and the assertion statements, where do we write them? So, as I told you, we need to write a test bench, a Vhdl code, another code, which has a special format. And I'm going to show you the format later on. So the test bench, as you know, we need to include the stimuli, or the stimuli are the test cases, using the wait statement and process and so on. And it includes as well the unit under test, or the design under test. The unit under test is your code, the code that we want to simulate. So for example, the AND gate. This is the unit under test. So this is what we want to test. Because this AND gate, we will include it in the test bench as a component. You will see later on. Do you know what is a component? Yeah, we used them before. So you will have your VHDL code, and you will include this as a component in the test bench. So this is how the test bench and your circuit or your main code will be linked. So your main code will be like a component now in the test bench. And the test bench, so this is what I'm just representing this with this small diagram here. So if this is your VHDL code, we have 2 inputs, 1 output. We will use this as a component in the test bench. And the test bench component, the test bench and architecture, but the entity will be empty, no ports. There will be no ports in the entity. We just declare the same ports of your circuit. We will declare them as signals with exactly the same names. And then we do the port mapping with those signals, and then we just write the test cases. So just to clarify further, so this is our, let's say that this is our code, VHDL code. For example, AND gate. So we will have the entity, we will have the architecture, and so on. You know those things, right? Now you need to go and create another code, which we call a VHDL test bench. So when you use the software tools, you will be able to add a test bench to your project, FPGA project. As you can see, the first thing that we do is an empty entity. And then we start the architecture. The architecture, as I told you, we declare this as a component. So this will be copy paste. This will be your component here in the test bench. And then signals, all ports that you have here will be declared as signals. So for example, if I have A, B, and C, you will have A, B, and C with exactly the same names. Again, this is a template that you need to follow. So we will declare it with exactly the same name, A, B, C, as signals. And then you do the port mapping with those. So you put A, B, C. And then this is part of the template. From here to here is all test benches should follow this. And then this is the place where we put the processes that we talk about, how to write the test cases. We put them here. But the rest is part of the template. And the good thing with the most of the software tools used with FPGAs or used to write Vhdl code is when you create a test bench, it will ask you, okay, what do you want to simulate? So you may have multiple files in your in your project. You may have multiple Vhdl files. For example, if you are working with components, so you have two components and then you have the main file. It will ask you, what do you want to simulate? So you select if you have just one file, an AND gate, let's say the AND gate, you will select the AND gate, the AND VHDL file. Once you select the AND VHDL file, all those what I have here will be inserted automatically. So you don't have to type those. They will be inserted automatically with the name of the port, because you have the names of the ports in your VHDL code, right? So everything will be inserted automatically. All what you need to do is just to write this part or the test cases, and that's it. But again, even if it's a software that doesn't include those automatically, it's very easy. You just have an empty entity architecture, and then you have this as a component, and then you just do the port mapping with the same names of the signals, and then you do your test cases. Let's take a simple example. Let's again with the AND gate. Let's say that I have this AND gate. This is the code for AND gate. Yeah, you know it. And I want to simulate this. I know it's very easy. It's clear that it's an AND gate, but just to show you for how does it work with test bench. Now, I will write the test bench. So as I said, the first thing that we need to do is to have an empty entity. So this is an empty entity. And then we start the architecture. And then this is the AND gate here. Do you see it's the entity, copy, paste. And the ports are A, B, and C. And then again, those signals, A, B, C. And then we do the port mapping. Of course, here you can just put A, B, C, right? As I told you, this is part of the template, sorry, the syntax. But you can just put A, B, C. Port map, A, B, C. And that's it. So this is the beginning, which is part of the template. Is this clear so far? Then
Yeah.
now I want to generate the test cases. Let's say that I want to do this. I want to have A0. I think here is until 100 nanosecond. This is in nanosecond, yeah. And then here we'll have 2. And by the way, what I have here is what I got, from the software when I ran the simulation. So let's say that in blue, this is what I want. So I need to write those cases. So I did A is equal 0. Here I use just one process. I showed you previously how to use 2 processes. Now I use 1 process. Then I do A is equal 0. A, and then B is equal 0. And then wait for 50 nanoseconds. So I did here. 0, 0. So what should be C? C should be 0. I added assert as well here. So I did assert C is equal 0. Report case 1 returns an error, severity error. So this means that now once you do those cases, if C is not 0, then show me this error. And then I do the same for all the remaining 4 cases. So I did again case 2, A is equal 0, B is equal 1, wait for 50 nanoseconds. And then I will repeat this again. So C should be 1. or 0 in this case as well. Third case, C should be 0, and fourth case, C should be 1. So I need to write 1 here. And that's it. So this code can be used to simulate the, and then I will run the simulation. The simulator will show you this. So it will display the A and B that you want, which you described here, and it will display as well the result of the simulation when it uses your code. Right, look what I did next. I just went to my test bench and I just put 1 instead of 0, which is wrong, right? For this case, for the first case, 0, 0, I should get C is equal 0, and I should write C equal 0 here. But let's say that by mistake I put C is equal 1. And then I ran the simulation. And this is what I got. I got this message displayed. Error, case 1 returns an error, which is good. So the code is correct, is an AND gate, but I got an error here. Because by mistake, I put 1 here instead of 0. So you need to be careful. And this is what I mentioned in the previous slide. When you use assert, you be careful. You have to make sure that what you expect is correct. If you put here what you expect is wrong, and even if the code is correct, it's an AND gate, it's fine, but it doesn't give you, it gives you this error. Right. That's it. I hope it's clear. I think we are done with this lecture.